So what do I mean by weird plots and graphs? You're familiar with something like this from math class. You have your x and y axes and some sort of function, right? But what if you see something more like this? Let's say you see a plot, but then you see another one, and another one, and another one, all on the same one. Are they just trying to save paper? No. This is actually a tricky way to show a three-dimensional graph. Because if you just draw one, it's a little bit awkward, as I'll show you, if you don't know what a 3D graph is. If you do know what a 3D graph is, you can see, not being able to rotate it, you only get one angle. It better be the right angle. But if you do it like this, it doesn't matter. Now, what's the difference between a plot and a graph? Basically nothing in this context. The words are used interchangeably all over the place. Often you'll see a plot is some points, and then you draw a line or a curve that describes the points, whereas a graph is just a line or curve in the first place. But it's not really that big of a difference. You'll see plot, you'll see graph all over the place. Just treat the two words as identical. So a plot, or a graph, you have your x-axis and your y-axis. Let's say y equals x squared. So it ends up looking like that. It's a parabola. Let's just say plus 2 since I drew it above the axis there. So you have two coordinates, two dimensions. This is flat, like a piece of paper. 3 dimensions, width, height, depth, x, y, z, that's our space around us. You can specify how much something to the left and right is, above and below is, forward and back is. It's all 3 dimensions. Piece of paper is 2 dimensions. When you have it this way, you have in algebra 2 variables, because you don't know what x is, you don't know what y is. But y is the result. You might even see f of x equals. F of x and y in this case are the same thing. You have x can be whatever. Let's say x is volts. And let's say whatever range. You care about 0 to 5 volts. So x can be 0, x can be 5, or anything in between, and it's volts, right? So y would be some other unit derived from volts using whatever math. So it's 2 dimensions, 2 variables, but it is a plot, a graph, in 2 dimensions of 1 variable effectively. So let's say we have here our volts axis, and this is our current axis. And we only care about 0 to 5, so this will be 5. And let's say we have Ohm's law. V equals IR, I times R. So since this is our y, I equals V divided by R. So this would be essentially F of V equals I is our y, V is our x. And R is not changing, R is just our resistor, so it would just be this. So V is the thing we're varying, and we're calculating I. We're not sitting here and going, I care about I from 0 to 5 amps, and going over that range. You could say 5 amps is here if you want, or whatever. But we're not sitting here and varying current. We're varying voltage and getting a result. This is always the last one, the y equals, the z equals. This is the thing we care about. This is the thing in your data sheet that you're interested in knowing based on other things you know. You might know how much base current you're supplying to a transistor. You might know how much voltage you're applying across the transistor, and you want to know, based on those two things that you are setting, how much current are you going to get through the transistor. So that would be your final calculated variable. So a plot's very simple. It's just a way to look at this sort of thing and get a feeling for, oh, like if you see a plot and it goes like this, you can say something's happening here. You can say this is a resonant frequency or whatever. You can say this is the good spot, and if I go too low or too high, it's going to get crappy. That's the purpose of a graph or plot or whatever. Now, before I show you 3D graphs, let me show you a 2D graph, because I've rambled quite a while and you're like, well, what's the point? Let's have our graph like this. All right, so this is your x and your y. Now, let's say you don't have access to a piece of paper. All you have is a line. All you have is a y-axis, and it looks like this. Or actually, we'll just rotate it so it looks better, right? So all you have is a y-axis. You have 1 dimension. You're trying to graph 2 dimensions in 1 dimension. Well, let's say we care about 0, let's say that's 5. We care about this region, so we don't care about that. This is what's relevant. Since it's a data sheet, we may not even have a graph over here, because that might be negative voltage. And it might just say, well, don't apply negative voltage. We're not going to give you a graph of that, because don't do it. It's going to break your thing. We don't need to show you what'll happen when you break the thing. It'll break. So that might be our plot. So let's say, and I'll make a little mark here to say this is 0. They're right there. It's just saying that's the 0 spot. That's there. Now, when x equals 0, y, let's say, is here, all right? If we just pick an x, y is there. So we'll say x equals 0. When x equals 5, y is up here. Let's say x equals 5. When x equals 1, it's here, x equals 1, or whatever. So it's two ways of showing the same thing. These points are here, let's say here, and let's say up here. We've just taken this and smushed it. And you see, if you were to take this and squish it into a line, just move them over, you'd get this. And then we're saying at these values, this is that. So you can still get an idea, not as good of an idea, it's not as easy to see immediately, but you still get an idea of what's happening to y as x changes. So if for whatever reason you wanted it on a line, you could do that. Now imagine if we have a 3D function, let's say z equals x squared plus y squared. Well, if I were to try to draw that, let's mark a 0 here, and try to go in 3 dimensions, it would kind of be a bowl like this, and then go up like this, and you can't see, it's already bad. Now, if you were doing this with a 3D modeling program, you'd get something you can see. It's like trying to draw a 3D video game scene or a movie or whatever. You can see 3 dimensions in 2 dimensions, but you're going to need some more sophisticated hardware than just randomly a hand unless you're a very good draftsman. But the point is, imagine I had drawn that well. You still get to see it from only one angle, right? Let's say there's all kinds of bumps and nodes and dips, and you want to see them, they're important. You want to rotate it, you want to look around. So now you've got to have it on the paper at different angles or try to draw it transparent so you can see through it. It's a mess. For a very simple function, it's not a problem. But once you get into interesting things like electrical properties, there's all kinds of bumps. But what if we did the same thing? We have 3 dimensions, but we want to draw them on 2 dimensions. Remember how we had y equals x whatever function of x, and we picked a value of x, calculated the y, drew a point. Picked another value of x, calculated a y, and drew a point for interesting values of x. Imagine we did that here. Imagine this is the z-axis. Z might be our collector current. In our example, we're trying to find how much collector current. X might be the base current we're supplying. Y might be the collector to emitter voltage we're supplying. Those are both things we control. And this is the collector current that we don't control. The transistor controls that. So we can change both of these, but we want to see what happens when we do. Well, let's say y equals 0. So this will be the x-axis. We're going to vary x and z, or rather vary x and find what z is for one particular y. Well, what is that? That's z equals x squared plus 0 squared equals x squared. That's a parabola. So we just get our nice parabola, and we write y equals 0 next to it to say if your whatever is 0, then this is what happens to your z as you change x. What about z equals x squared plus 1 squared? So now y is 1 equals x squared plus 1. Well, now we get a line here, and we say y equals 1. What if we say z equals x squared plus 2 squared? That's x squared equals 4. And that's up here. Y equals 2. So what just happened? We're basically taking a slice. X squared plus y squared equals z. That's a bowl, essentially. It's a parabola, and you spin it. Looks like a bowl. But if you slice it, you get parabolas. You get parabolas going up the sides. All right? Don't worry about that too much. But can you see how it encodes the information, right? You've got the bottom of the bowl, and then the sides go up, because the only part of the bowl, see this bowl? At the bottom, at the center, would be there. And then as you go up the sides, you see that it no longer touches, like if you took a slice this way, right? You took a slice that way, you can see it's a parabola that goes all the way to the bottom. But then if you moved over, it goes up the side a bit. And if you moved over still, it goes up the side a bit. See? Like here's one slice of it. So we're just moving over in one dimension and taking slices. And it still encodes information. You can see, where it starts, and you can see we're varying y by 1 and then 1 again, but this gap is smaller than this gap, so it's exploding upward. So the full plot in the data sheet might look something like this. You might see like this, and then like this, and then like this, and then it might show it all the way up here. That might be the full thing. And you would say y equals 0, y equals 1, y equals 2, y equals 3. So it gives you an idea of what's going on. That's what these plots are. They're slices. So let me show you an actual one of these and walk through it. So this is a three-dimensional space. Let's say you've got your x here, your y here, and your z here. If z equals x squared plus y squared, do you see there's your bowl? You see how it's kind of a bowl? Gets wider as it goes up, it cups, it's like a bowl. But what if I say z equals x squared plus 0 squared? Do you kind of see how it cuts it? Let me change the color. Zoom in a bit too so it's a little more clear. Do you see when I go from this angle, see how it's a parabola? See how it cuts it? So when that variable is 0, it's this parabola, this parabola, this parabola. And right here, see the red line going up? That's where it cuts it. That's where this bowl is that value. And if I go, instead of 0 squared, I do 1 squared. Now, do you see it's up a little bit? Look at how it kind of cuts it higher. If I have just a little bit of it showing, it's this in here. So now this bowl, it's being cut higher and a little in, but it keeps going up. If I change it to 2 squared, and now I have to zoom out because it went higher. See way up there? See, now it's cutting it up there. And we plot that cut there. That's basically where we're getting these lines from. Now let me show you an actual datasheet. The venerable, my favorite 2N3904 semiconductor, transistor, NPN-BJT. So here's our datasheet, and if we scroll down, we'll go through these ratings and circuit diagrams, and then we start seeing these plots. So for example, here we see collector current on the horizontal axis, time on the vertical axis, and each of these graphs is voltages. So it's a three-dimensional plot, and you can see how it might curve a little bit, but let me show you the one that's interesting, which is collector saturation region. Let me try and zoom in a bit here. So let's take a look at this plot here. So on the horizontal axis, and you'll notice we have 0.1 and 1 over here, and there's these lines that get larger and smaller, wider and narrower. That indicates a logarithmic plot. We've gone over that, but don't worry about that right now. It's just a horizontal axis. IB, base current in milliamps. So this is the base current. We're setting this based on the voltage and the resistance and whatever is going on at the base. We are controlling the base current. So these are values that we set in our circuit. Similarly, on the vertical axis, it says VCE, collector emitter voltage, in volts. So that's the voltage we apply across the collector to emitter. The through voltage, the work voltage, whatever you want to call it. We also control that. We just apply the voltage, and there it is. So we control the base current, and we control the emitter voltage. We vary two different things. And then these plots, right, IC, that's collector current. That's the current going into the collector. That's what's determined by the transistor. That's what we're trying to find. And we have 1 milliamp, 10 milliamps, 30 milliamps, 100 milliamps. And it just says this is operating at 25 degrees Celsius for the whole plot. Now, just look at this one line. What does this mean? If we are aiming for a collector current of 1 milliamp, and then we are supplying, let's say, 0.6 volts across the collector to emitter, there's a spot. Then we look down and we see this much base current. If we want this collector current and we want to give it this voltage, then we have to give it this base current. Or if we want this collector current and we want to give this base current, then we go up and see we can give it a voltage anywhere along here. And this implies, because it's a nice vertical line, it implies it goes straight up. So let's say we want 1 milliamp collector current. We're going to give it about 0.02 milliamps base current, which means we have to give it at least 0.4 volts across the collector to emitter. Anything from 0.4 up should give us that. But look over here. If we want 10 milliamps, we got to give it 0.1 and apply at least, let's say, 0.5 for safety. Go way over here. We want 100 milliamps into the collector. Then we apply 5 milliamps. Then we only need 0.4 volts. But if we're only applying 0.3 milliamps, remember this current, the base current, might be a signal coming in. You might be limited by how much power can be drawn out of the source. So let's say you could only do 3 milliamps. You can't draw any more than 3 milliamps or you're going to burn out the source, or it just won't give you more than 3. Well, now you say, well, I need 100 milliamps out of this. So I'm going to have to supply at least a volt all the way up here, 100 milliamps, at least a volt. But let's say you don't have a volt. Let's say you could only apply 0.8 volts. Well, you're not going to get there. The graph hasn't gotten there yet, see? So that tells you you're going to need 2 amplification stages. You're going to have to amplify it up to about there, and then amplify it again, for example. Now, what if you need 20 milliamps? Well, that's in here somewhere. But the point is it gives you a general idea, because you see the shape of these graphs. These graphs are roughly the same shape. So you can see that the more base current you supply, the less collector emitter voltage you need to supply to get a certain current. But it goes up very fast if you're supplying a very small voltage, because this is logarithmic. See here, you apply this small base current and you'll get the collector current you want for any voltage high or low up to this minimum spot. But you can't go lower. If you need this current, you can't go lower. But if you need to supply less voltage, then it goes up fast, really fast, faster and faster. So this graph tells you you need a certain minimum voltage across your collector to emitter, or you're going to need a humongous amount of current on the base to the point you probably burn your transistor out, or your source can't supply it. Similarly, it tells you for the current, you're going to be able to turn down the base current to a certain level and still get your current, right? Because if you need 1 milliamp and you're supplying voltage that's way up here, this line is going to be up there. So anywhere along this point, so you can turn it down and down and down and down and down to about here. Let's say that's safe, because transistors are variant. Warmer, colder, slightly different construction, there can be a little wiggle. But it tells you that you can turn your base current way down, and at a certain point, it'll just stop, and the current is not going to change. Or you can look at it another way. You can say, okay, well, here's my base current, and as I change the voltage, it's not changing the current. So if I have 0.2, and then I increase the volts up, it's not increasing the current. Apply 9 volts is not going to increase the current. It's complex. This one single graph tells you 80 different things, but you can get an idea from looking at how it changes. But that's what these plots are. That's how they work, is just slices. And you visually interpret between the slices. You can see 10 milliamp curve is this, 30 milliamp curve is this. So the 20 milliamp curve is going to be somewhere in between. So you can just mentally or take a pen or something and draw a line in between, and that gives you a rough idea. It's just meant to give you a basic idea of what's going on. And then you have to do a few more experiments. Let's look at this one. The DC current gain, collector current, and the current gain. So collector current is how much current is going into the collector. Gain is how much that's amplified from the base current, right? So whatever base current you supplied, you're getting this much collector current. And then this is a plot of how much that's increased from the base. And then you've got different plots of temperature. So at minus 55°C, you're getting less gain. At plus 25°C normal room temperature, you're getting more gain. Higher temperature still, you're getting still more gain. So you can see that higher temperature means everything's moving faster, you're getting better values if you're not changing the collector to emitter voltage. But then you look over here and you see you go down here to basically no gain. In short, these weird plots with multiple lines are just a way to represent 2 variables, 2 things you can change, when all you have to do that is a sheet of paper. They require extra interpretation, and it would be better if you could be on a computer with a nice 3D plot that you could spin and zoom and click on for values and all that other stuff. But this is a data sheet, and all of this started, when personal computers weren't even a thing. Data sheets precede the personal computer, and this is just how you did it. I promise, once you get used to it, it's not that bad. It adds to the learning curve, but once you do the learning, you're good. So while you squint at a whole bunch of squiggly lines, I'll be seeing you.